Okay, so we're moving on to chapter 15, differentials. Our goal in this chapter is to define the tangent bundle as a locally free sheaf, or in other words, a vector bundle. And the fibers of this vector bundle will be the tangent spaces. So this is going to be a way to put all the tangent spaces together into a vector bundle, or a locally free sheaf, is more in our language. And remember, what's the fiber of a locally free sheaf? Well, you take a point of your variety or your scheme, and then you look at the stock, and then you mod out by the maximal ideal. That'll give you a vector space. So I think we talked about that last time. A vector space over the residue field at that point, and that's called the fiber. And then we're going to show that we can make this tangent bundle so that the fibers are actually the tangent spaces at the point, and they vary the way that tangent spaces should as you move around on the space. All right, so that's the goal here. Okay, and then the other thing we're going to do is hopefully compute some examples. And we'll see that this is a powerful and a commonly used tool, the idea of the tangent bundle and the associated canonical bundle, which we'll talk about when you're trying to classify varieties or try to tell two different varieties apart. You can, because every variety has a tangent bundle, is something you can always use, and then you can use properties of the tangent bundle to tell whether two varieties are isomorphic or not. So hopefully we'll see some examples of that. All right, we're only going to do this for for varieties over a field. Remember, we only define the tangent space for varieties. There is notions of tangent space for general schemes, but we'll focus on varieties. That's where it's sort of used the most. All right, so we're going to start out with this definition. This is just going to be sort of an affine definition just for commutative algebra. So let's start with our K algebra. Okay, and we will define omega r to be the free R module generated by symbols df for all f in R. All right, so this is basically what we're going to say. We want a way to take differentials of elements of our K algebra. Okay. Okay. Sorry. So the definition is not done yet. So we need to go modulo the relations. So we want to impose the relations that we sort of expect from derivatives. So first, it should be linear. So a df plus g needs to be equal to df plus dg. And then it should obey sort of this Leibniz product rule. So this is f times dg plus g times df. All right, so this is an R module, so it makes, these symbols df are part of an R module, so it makes sense to multiply them by f and g. Okay, and finally, df should be 0 for all f in k. So if your f is just a constant from the field, then its differential is 0. All right, so these are all familiar properties of derivatives that should make sense to you. All right, so once we have that, okay, well, let's give this a name first here. So omega r is the module of differentials. Okay, and an element df is called a differential. Okay, and there's a morphism, right, from r to omega r. That's just d, right? That just sends a f to df. Okay, this is a k linear map, but it's not an R module homomorphism. Okay, of course it's not a homomorphism because it doesn't respect the products. It obeys rather this product rule instead. That's not what homomorphisms do, but it is k-linear. Okay, so it's just a vector space map. All right, so this is our module of differentials. Let's next think about how this construction behaves with respect to localization. So now let's let a P be a prime ideal in R. So remember, R is a K algebra, and let's look at omega R localized at P, and try and think about what happens to a quotient like dg over f, right? In this module here. Well, here's one way to do it. We know that a 0 has to be equal to d of 1 over f times f, all right, because that's just the derivative of a constant. Then by the product rule, this will be 1 over f df plus f times d of 1 over f. All right, so that tells me now that d of 1 over f has to be equal to minus 1 over f squared times df. All right, and so now we basically have what we need here to do this. This is, of course, just 1 over f dg, again by the product rule, plus g times d1 over f. But we know what d1 over f is f squared df. Like that. Okay. So there's our formula here, and of course this is just the so-called quotient rule that you learned in first semester calculus. All right, but it follows from just using these three axioms here. Okay, what's the point of this? This computation shows us that this construction commutes with localization. All right, so this is isomorphic to our localized at P. All right, just to sketch that isomorphism, I mean, there's clearly a map this way, right? Because any symbol you write down in here will be a valid symbol that you could write down over here. The interesting part is to show that that's surjective because there's things in here like D, F over G. These are not symbols that come up in here. But according to our formula up here, you can write this in terms of these dg and df, those are generators in omega r, and then the coefficients are things in the localization from rp. Okay, so that's how that goes. Now, what's the good thing about this? Well, so on spec r, we can form a sheaf of modules, omega r tilde, right? Because remember, omega r is an R module, so that makes sense. And let's recall that regular functions are given by elements phi p and rp satisfying some compatibility conditions, like locally they have to be given by polynomials, right? And so okay, let me write this. And sections of omega r tilde are given by psi p and omega r localized at P. So we have a differential map, right? D, which just takes phi P maps to D phi P, right? This is in RP, and this is in omega r localized at P, which is the same as omega r P. Okay, so the point is here we have a map. So we have differentials of regular functions. So this is D that takes a sheaf of regular functions into omega. Well, okay, let me write this. D O spec r into omega r. Okay, and once again, this is D is only k linear, so it's not morphism of sheaves of modules. Okay, and the point here is right. The map D from RP goes into omega RP, but the point was that that's isomorphic to the stock of the sheaf, so you get something well defined like you want. All right, let's do an example. So let's have R be the K algebra. It's just the polynomial ring in n variables. Okay, so the axioms of the differentials that we mentioned before give us basically all the familiar rules from calculus. So we get the product rule, power rule. I think that's all we need here. So for example, d f will just be df d x1 times dx1 plus df dx x2 dx2 plus dot dot dot. Okay, up to the end. Okay, so if you just apply the rules over and over again, you can reduce it down to this until you just have dx's dx1, and then there's no rules to apply here, right? Because x is not the product of anything, and it's you already used the linearity and everything. So so you keep reducing it, and you'll end up getting something like this. All right, and in fact, there's no sort of other relations, so you can think about that. So in fact, omega r is actually just the free module generated by the dxi. All right. All right. So that's the first example. For part B, well, let's have R now be the same polynomial ring, but we'll quotient out by an ideal. So I in, well, let me just say I is an ideal. Okay, so it's still generated by, for the same reason, it's still generated by dx1 up through dxn, but there's some extra relations, right? But we know that f equals 0 for any F and I. So also that means that DF has to be 0, right? So we get that, and it turns out that's basically all the relations you need. You only need to put in the df equals 0 for any f and I, and so you get r dx plus r dxn, and then you have to quotient out by things that look like this: dfi dxj times dxj. Um, for I equals 1 up to n. Or up to m. And where the fi here are the generators of the ideal. All right, so you only need to do the generators, and that will give you all the relations that you need. Okay, so that's a fairly concrete description of what this module looks like. Let's now sort of take a fiber, right, and see what the fibers look like. So in taking a fiber, a sheaf corresponds in algebra to tensoring with R mod P, where P is a maximal ideal. So let's let P be a maximal ideal. All right, and so R mod P will just be isomorphic to the base field. All right, so if we do this tensor, then we'll just have a vector space generated by the symbols dx1 through dxn, and then we'll have to mod out by what happens to these functions here when you tensor by R mod P. Well, that basically just amounts to evaluating the polynomials at P, right? So this will be dfi dxi evaluated at the point P times the symbol dxi. Let's see, I think I better fix my indices here. So that probably should be a J, and that should be a J, and then I'll make this a J. All right, I think that's right. Okay, again for I equals 1 m, and this is J equals 110. Okay, and this is going to be interesting to us because we're interested in the tangent space. So let's recall before, so you can look back at the proof. I think it's in back in chapter 10 maybe. We had the Jacobian matrix. So J is the Jacobian matrix. It's just a matrix of partial derivatives. And you could think of it as mapping Kn to Km, right, where n is the number of variables. So this n here is corresponding to x1 through xn, the coordinates on our space, and this m is corresponding to the number of generators of our ideal. So we had a map here, and we observed back in that chapter that the tangent space was exactly the kernel of this map. Okay, so you can look back at that proof if you don't remember that. Now we have something very similar here. So you'll notice here, these things here are exactly the entries of the Jacobian matrix, but things are kind of going the wrong way, sort of. We have here instead we have our n-dimensional vector space, and then we're quotienting out by m things. So that's kind of backwards here. So we basically want to take the dual of everything here. So if we take km dual and a kn dual, then this is what we want. We'll have a surjective map here where we have an n-dimensional vector space and we're taking a quotient by m generators. So that's exactly what we have. We have n things here and we're quotienting out by m things here, and so so we get exactly that fiber. of this sheaf of differentials is isomorphic to the tangent space at P. Sorry, the dual of the tangent space. Okay, so that's our big thing here. So now we've got our construction of the tangent bundle, or rather the construction of the dual of the tangent bundle. So we'll call this the cotangent bundle. So omega r tilde will be the cotangent sheaf. On spec r. All right, so the next thing we would really like to do is sort of glue all these definitions together into something on an arbitrary variety. So how are we going to do that? Well, it turns out there's a nicer kind of global description. So I think I'll kind of just summarize it, because it turns out that this local description is the thing that you really want to use if you're doing any sort of computations or something. But let me just quickly describe the global construction. All right, so first we need this lemma. So once again, R is a K algebra, and let's consider the map of delta from R tensor over K with R into R, and it's just a multiplication map, right? F tensor G maps to F times G. And then the lemma says that the kernel of delta, okay, well, listen, sorry, let me back up. Let's let J be equal to the kernel of this map. And then the lemma says J mod J squared is isomorphic to omega r. All right, so I'm just going to leave the proof to you if you're interested in a fairly straightforward algebra, I think. All right, but then that leads us to our global construction here. So so let's let X be a variety, not necessarily affine. And let's let the diagonal, the triangle, the delta X is a diagonal. And recall by the definition of a variety that it's going to be closed. All right, so it has an ideal sheaf. So let's let script di be the ideal sheaf of omega x, or sorry, of delta x in the product. All right, so I think we talked about how a closed subvariety has a corresponding ideal sheaf. Okay, and let's give a name to the inclusion map. So I will be the map that takes the diagonal into the product. And so remember, I is a sheaf on the product. Right, it's the sheaf of functions that vanish on the diagonal. And so what we're going to do is we're going to take I mod I squared. So you can think about why that makes sense to do that with a sheaf of modules. And then we'll just pull it back to the diagonal, right? And remember that the diagonal is isomorphic to x itself. So let me write that over here. So the diagonal is of course isomorphic to x. So this thing here, after composing with this isomorphism, we'll call this omega x. All right. So the point of this construction is if you restrict to the affine case, or take an affine open cover, then this thing that we just did corresponds exactly to what we did in this lemma here, right? So R tensor R mapping to R. Remember that this corresponds to this will correspond to the product, the diagonal inclusion spec R mapping into spec R cross spec R. All right, so if you remember, the way we constructed products of varieties was by taking, for affine varieties, is by taking tensor products of the coordinate rings. So that's exactly what you want, and you can think about why the diagonal inclusion corresponds to this multiplication map, and then the kernel is exactly the ideal sheaf. Okay, so we have this global description here. If you restrict any affine set, it reduces to this thing here, which the lemma, which we didn't prove, shows that that's isomorphic to omega r, which is maybe which is our original definition of differentials that we liked, that we could get our hands on and work with. Okay, so that's how you do it for general varieties. Okay, and then just as before, this is going to be called the cotangent sheaf. All right, so we talked about how the cotangent sheaf is supposed to be the dual of the tangent sheaf. So let's make that just a little bit more precise here. So proposition. So let X be variety of pure dimension n. All right. Then the cotangent sheaf of X is locally free of rank n if and only if X is smooth. All right, so this is an important proposition, but let's do the proof really quick, or at least part of the proof. So one direction is easy. So let's do this direction. So if omega x is locally free of rank n, then the fibers at any point p, so p smooth, or sorry, not a smooth point, but a closed point of x, has dimension n. Right, because it's locally free of rank n, so all the fibers have dimension n, right? And that implies that the tangent space has dimension n. And remember, that was basically our definition of smooth, was that the tangent space had the same dimension as the variety. So smooth at p. All right. The other direction, it takes a little bit more work, so maybe I won't write it down, but you can read it in the notes if you're interested. Okay, so finally, let's give our definition of the tangent sheaf. So if x is smooth, then the tangent sheaf Tx is defined to be just the dual of the cotangent sheaf. All right, so for a locally free sheaf, it makes sense to take the dual, and it's again a locally free sheaf of rank n. Okay, I mean you can take the dual, even if it's not locally free, but then you won't get, it won't be as nice. When you take the dual locally free things, you get another locally free thing of the same rank, and you don't lose any information. All right, one more definition here: the canonical bundle of X is the line bundle usually written as omega subscript x, and it's defined to be the top wedge power of the cotangent bundle. All right, so it's a line bundle. It's a rank 1 locally free sheaf. And the good thing is that every smooth variety has a canonical bundle. So you can study smooth varieties by properties of their canonical bundle. Of course, the cotangent bundle has even more information, but line bundles are easier to study and have maybe simpler properties. So you might want to start by thinking about the canonical bundle, and we'll hopefully compute some examples of the canonical bundle tomorrow and see how that works. Okay, so that's all I'm going to say for today.